All right. Welcome to our third machine learning series seminar of the spring. This is our final one for this spring, and we're really happy to have Sarah Brown from the University of Rhode Island to talk on machine learning problems for fairness. And of course, this is an important topic in machine learning, is to make sure that the models not only predict well, but that they're also fair to all possible users. Sarah is an assistant professor of computer science, and she's director of the ML4 STS lab at the University of Rhode Island. She was a data science initiative postdoc at Brown before that. And she worked with Bjorn Sandstede and completed a chancellor's postdoctoral fellow in computer science before that at the University of California, Berkeley, working with Professor Mike Jordan. She completed a bachelor's degree in electrical engineering and with a minor in biomedical engineering, and a master's in electrical and computer engineering and a PhD in electrical engineering. So she has a long background in this area, working at Northeastern University. We are really happy to have Sarah here today, and I'm going to not say anything more so that she has as much time as possible. And if you've got questions, you can put them in the chat, and we'll hold those for the end. So Sarah, go ahead.
All right, thank you for having me, and I'm really excited to share this work. We're talking about how do we assess machine learning problems for fairness before we fit the model. And to do this, we will start with why do we need to think about fairness in machine learning? And one example is this case was called Gender Shades. And Timney Gabriel and Joy Bolomini audited a bunch of facial recognition systems that provided as a feature, you give it a face, it would tell you the gender. And they found large disparities in how accurate it was, depending on the skin tone of the person, as rated by trained dermatologists, and the person's gender identity. They built this through a parliamentary data set. So they found parliamentary people who they knew their identities, they knew all the things, they're balanced from different countries, and they found this huge disparity. There's other cases as well. So one case that's a really famous case in fairness and machine learning, we talk about it a lot, was the COMPASS algorithm. This is an algorithm that is still used by lots of police departments across the country. And in 2016, our journalists at ProPublica published an audit of the algorithm. And the way they did that was they took 2 years worth of every person in one county in Florida, Broward County, Florida, who had been arrested, and they got a score from the algorithm. And then they did that for 2013, 2014, and then for every single person, or 2012 to 2014, and then for every single one of those people, they knew the actual what had happened for 2 years later, because they were doing the study more than 2 years after their arrests. And they found huge disparities in what type of mistakes it made. So even when the first sanity check of is it equally accurate for Black and white people did pass, when they dug deeper and looked at what type of mistake it made, it would often be incorrect about white people, saying they're low risk when they did get rearrested. And then when it was wrong about a Black person, it was typically that they were rated high risk and then they did not get rearrested within 2 years. So these are starting to have kind of big problems in there. And this occurs in other contexts as well. So this 2019 paper, looking at an algorithm that was used in a healthcare system, the goal of the system was to help the hospital better put the right patients into their managed care program. So they wanted to give people extra help navigating hospital systems, because hospitals are complicated and not easy for people. And what they found was a large disparity in how actually sick 2 patients were when the algorithm gave them the same risk score. And they were using this system, the hospital was actually using the risk score to decide to automatically enroll people in extra help or to flag them for their doctor to enroll them. And so the disparity in who was getting enrolled in the program, who was actually getting access to this extra help to navigate the system, to manage their chronic conditions, was very large. This one starts to give us some hope, because what these researchers also found was that given the data that the company that made the machine learning algorithm already had, a slight shift in how they set up the model, how they set up the problem, could make a big difference. And this was a different change than what machine learning researchers tend to do. Because as a machine learning researcher, the way we've proceeded to mostly look at how do we fix machine learning algorithms being biased is we focus on, well, how do I change my algorithm? How do I change the learning step? How do I learn a different problem? How do I constrain it or smooth it or regularize it to make my solution meet the different goals I want? So machine learning has approached fairness in very much the same way we approach overfitting. And so some people are like, oh, it's just the data. If you just got me better data, it'd be better. Others look, well, okay, the data is the problem. We'll pre-process it. We can ship the features or normalize things, and that'll make it better. And it works sometimes. Others, in cases like disparities in credit scores, they do post-processing. So they change how they use the model. And the most common one is this in-processing. So we just change the algorithm, we add a regularizer. So it's literally the same techniques we use to fit overfitting or, deal with outliers, they're applying to fairness. And it works sometimes, but we have no clear ways of when to do what or how to do it. And when we think about the bigger picture, all of these techniques are dependent on us writing a particular definition of fairness, and we optimize for that one thing. And that's a normative judgment that is not what the data scientists are trained to do. We probably should be training data scientists better, but they're not currently, that's not what their skill set is at, that's not what they're doing. And so what I'm proposing is, as an alternative strategy, that we reformulate the problem before we fit the model. So that the way we set up the problem, what we feed to the algorithm, is better at producing a fair algorithm. So, and this is also motivated, so the Obermeyer thing, they changed how they set it up, and that worked. It's also motivated by the idea that a lot of social critiques of the results in fair machine learning is that, well, maybe sometimes you shouldn't build the thing at all, because that's just never going to be fair. We go back to that facial gender recognition case. What ultimately happened is that some of those companies have now just removed the feature of predicting gender. Some of them were able to remove the disparity because they trained it differently, they figured something out, and others accepted that there's no reason to predict gender from faces, right? It's not the right task. We shouldn't be doing it at all. And it's always going to be, there's always going to be this disparity in the performance, and so we just shouldn't do it. But to date, there's been no technical work that helps a data scientist who's working on a problem decide whether should it just be something we shouldn't do because fundamentally we shouldn't do it, or is it that we just haven't set the problem up right and we should fix it? So the gender recognition case we just shouldn't do because it's not a real thing that exists in faces. And the Obermeyer case was, if they reformulated and used a different combination, used the variables they already had in a slightly different way, they were able to get a fair outcome. And so differentiating those cases there's no techniques that are standard to do that. What I'm going to talk about is a way to do that. And if we look back at the Obermeyer example in detail, this is kind of what they saw. So these are their figures. And so the first plot on the left-hand side shows us that the risk score and the total medical expenditures, which is what they use as a proxy to train the algorithm. So they've used total healthcare expenditures as a guess, an approximation for how totally sick someone was. They trained the model, and you can see for Black and white people, the yellow and purple lines are they're pretty close to each other. They go up and down. They're very tightly together. But if you switch and you look at how sick people are, number of total chronic illnesses, versus those mean total medical expenditure, so the same vertical axis, but you compare to sickness, how sick people are, two people that are the same sickness spend very different amounts of money based on race. And that then showed up when they looked at all the different laboratory measures. based on their risk score. So if you plot the risk score versus how sick a patient actually was, they have these huge disparities on almost all of the measures. So the key point from these plots is this: that the purple line and the yellow line are they're not touching in most cases. They're only related on one of the measures, and on most of the other measures, there's fairly large gaps here. And what they did was they trained instead using the total number of active chronic conditions. In that case, there's some disparity in how well the algorithm performs at predicting the thing, but in the right-hand plot, the percentage of Black people who get defaulted into or admitted into the program to get extra support is significantly increased. So it increases from a maximum of less than 20% to nearly 50% of the Black patients were being recommended at the very highest end of the risk scores, were being recommended for this managed care. And so part of the reason that the audit had occurred was that the doctors, the hospital administrators were like, we think this program should be helping more Black people, but it's not because the risk scores aren't doing it, so what's going on? And so this showed that by retraining, the first proxy of is it fair actually looks worse because it performs more differently for the two groups of people, but it starts to give outcomes that were more what the doctors were expecting. And so what this starts to get into is that sometimes the ways that the standard techniques we use for measuring the performance of a machine learning model, the way we set the problem up, what we define as success for the model, isn't always exactly what the success in the real world really means. And so we need better ways to negotiate that trade-off. And so how do we do this? How do we choose when to reformulate? And what I'm proposing is these computationally efficient information theoretic quantities for evaluating the setup. So before we put the model, we'll evaluate the problem setup with some cheap, easy to compute things. So we don't have to fit tons of models and wait for them to train and do all of those things. And we can decide to either proceed as we are, reformulate, or we have the option because we haven't even trained the model, doesn't exist yet. It's much easier to say, oh, we just won't build this one. And so the way the rest of the talk will go is I'll give a little background on information theory to kind of build up the intuition for what we're doing. I'll spend a little time formalizing what happens before we fit a machine learning model. And then I'll show my formulations that I worked on with my PhD student and our experimental results so far. So the reason we want to use information theory is that it's designed to capture sort of general signals, how they're related to one another. It's very principled. It requires sort of protoformalization, and it relies on sort of probability things, but it's also pretty easy to build intuition for and kind of convey to people that maybe aren't familiar with the detailed underlying mathematics. And so to start building that intuition up, it originated, we're using sort of Shannon entropy. So it originated in people trying to send signals from point A to point B over a wire. It was AT&T Bell Labs. And so the information in a single variable is related to its total entropy. So how much does this variable change? If the variable is the same all the time, it doesn't tell us anything, right? There's no information. If that variable could vary a lot, it has a higher capacity for being informative of something. We can have that for one variable or another variable. In a machine learning case, we have some features, the measurements that we want to use to predict an outcome Y. And then the mutual information is the thing that we're most interested in, which is how much do those variables tell us the same thing? So how much does knowing one mean we know the other, and vice versa? It's not directional. We can use it in either direction. It's just how much do these variables tell the same thing? In machine learning, our goal is to make sure that that middle purple part there, the mutual information between X and Y, is as high as possible. That's what we want in a good machine learning problem. So we want this. And formally, it's written down with these equations. The details of the equations are not essential to understanding. The most important things to notice in these equations is that it relies on us knowing what the distribution of the variables are. So we need to know how the features are distributed and how the labels are distributed. And then it can be written in two ways. We can write it as this sum on the top, or we can write it in terms of a distance in the bottom. And the key thing here is that second equation could equivalently be read as that the mutual information is how far away the actual distribution, joint distribution of two variables is from what it would be if they were completely unrelated. So we can think of the mutual information then as a condition of how related two variables are. And if the mutual information is 0, it means that the variables are statistically uncorrelated completely. If it's very high, that means they share the same information. So mutual information can be interpreted intuitively, sort of like a correlation, but it doesn't have all the strict assumptions of like a linear correlation. So we don't need the variables to be linearly distributed. There's no Gaussianity assumption. The relationship between them can be whatever it happens to be, and the mutual information will capture that dependency there. We can also do this conditionally. And so this is a very nice formal way of describing the relationships you want to have in variables. And so how do we apply that into a task for machine learning? So when we start, we say we want to build a machine learning algorithm, the first thing we think is, let's predict some concept, and we're going to call that concept Z. We'll call this the idealized task. So in the Obermeyer example, what they want to predict is who needs the most help managing their health, right? Who should be enrolled in the managed healthcare? So who they want to predict and rank the patients, or give them a score of how badly they need extra help. If it's a bank, they want to predict who will pay them back a loan. And then we have to think, well, how would we even do that? In an ideal world, like what would we even do? So what would we need to get? How would we have to do that? And so we want to find, hopefully there's some plausible set of features, some things we can measure that we could use to make this prediction. And we hope that those are related, right? The mutual information between those is going to be high. And then we have to say, can we really do that? So we can't measure. There's no thing you can just go into the world with a sensor and say, oh, this is how badly the person needs the managed care. Or what probability with which this person's going to repay their loan. That doesn't exist as a thing we can actually measure. So we can't actually get a Z. The Z thing, the variable, it's a thing we wish we had in our hearts. It exists in our minds, but it does not exist in our data. So we use some proxy target Y instead. And the features we wish we had, a full description of the patient's health, or everything about a person's past interactions with credit, is also not measurable. You have some subset of that. That's what you can actually get. So again, if you think about these steps in the Obermeyer example, Z is how much a person needs the managed care. X would be everything about their full picture of their health, and possibly some socioeconomic status information as well, because that would kind of dictate someone who's highly educated and understands how the healthcare system works, even if they're in poor health, may not need the managed care as much as someone who does not understand the system and has chronic conditions, right? They would have varying needs depending on things outside of their health. But what we actually have is an electronic health record, which has many problems. People change hospitals. They don't go to the hospital for everything that happens. They go to multiple doctors. Sometimes they go to urgent care. Sometimes whatever, right? There's all these different gaps. Sometimes the handwriting cannot be translated into the digital record well. All sorts of things go wrong with electronic health records that make them a partial picture. And in the Obermeyer case, the data scientist chose to approximate a person's total health with how much they had spent on healthcare in the previous year. Maybe that's obvious that it would have racial disparities, but it wasn't, they didn't detect that beforehand. So what do we do now that we have this set up? So again, these are the tasks. We have the idealized task, and we have this plausible task, what we want to do, and finally we have the realized task. And the realized task, the most important thing to take away here is that this realized task is something we can manipulate. Most machine learning research, however, considers the data set and therefore the task fixed. So we just assume, oh, we got a data set, it fell from the sky. Now we do machine learning. We don't always think about how do we manipulate that and how can we change it. So that's where this work comes in, and our contribution here is these information theoretic task fairness quantities. So the idea is to measure the fairness in some way before we fit a model. So rather than measuring fairness in the disparities of performance of the model that we've made, we'll measure the capacity of the data to even enable our algorithms that we have to produce fair outcomes. So to do this, we go back to the classical fairness criteria. So these are fairness criteria that have been used in various forms in machine learning and in other contexts. So a lot of these have by different names and different approximations and different minor tweaks to them, but they've been used in educational testing, like educational psychology literature for like many decades, like since the 70s-ish. So there's 3 basic groups of them, and conveniently, they're all easy to write in terms of mutual information. So if we have A, which is our protected attribute, or for example, race or gender, something about some demographic variables that we don't want our outcomes to be reliant on. We want to be fair with respect to that. And then we have the model or the predictor's performance is y hat, and the variable we use to set up our model is y. Independent says we just want no relationship between what our model predicts and the race or the gender, right? We want those to be just unrelated completely. No exceptions, unrelated. Separation and sufficiency soften that in 2 different ways. Separation says that if we condition on the truth as we measured it, then we want that relationship to go away. So if we go back to one of our examples to think about what that one means, if we take the compass example, separation says that if we condition on what actually happened, who got arrested and who didn't get arrested after 2 years, then the model's predictions, the distribution of scores, of risk scores, should be unrelated to race. So among the people who did get rearrested, there should be the same distribution of different scores for Black and white people, and among the people who were not rearrested, there should be the same distribution of scores for Black and white people. But if you mix it all together, that it's okay if they're not there. But as long as when you condition, it's okay, is what separation says. And sufficiency goes the other way. So let's split people based on the model's predictions and then see if the truth is still related. So we take all the people that were given a score of 10 and we see if the same percentage of them were rearrested or not. All the people who were given a score of 9 on a scale of 1 to 10 were the same percentage rearrested and not for each score down. These are 3 different criteria. The journalists in the ProPublica example used separation, and they found Compass was not fair with respect to that. The people who built it thought that it should be fair with respect to sufficiency. And even using ProPublica's own data, it does show up doing that. So we have these tensions. We can't actually have all of these things at once. We have to make a choice when we fit the models this way. So the first thing we did was we took these classical fairness definitions and we thought of ways to translate them we could apply them before we fit the model. So we want to get rid of that y hat and replace it with something that we have before we fit a model. And so we provide 4 criteria. So we have the feature independence. So we just want the features to be completely unrelated to the protected attributes. This sounds great. It's also never true. So the world, just about everything in our world is related to race and gender. Whether we think it should be or not, a lot of it is. The next criterion might be, we want whatever we choose as our approximation, we want that to be as unrelated. We want that to be completely unrelated. Again, it's not going to happen completely, but maybe we can try to minimize it or something else. The separation, if we condition on the outcome we're predicting, are then the features unrelated to the demographics. And in this case, now the sufficiency criterion starts to be obviously really, really challenging. Because conditioning on the features, so conditioned on all of my independent variables in my system, I want the outcomes to be unrelated to the protected attribute. And that is very, very difficult to calculate. So for most of the rest of the talk, we won't come back to the sufficiency criterion, but that works out to be okay, because the main motivation for the sufficiency criterion is that in the case of a model's prediction, the prediction occurs in time, temporally, before the actual outcome. So the model, the COMPASS algorithm gave the person a score before it was determined whether they were rearrested within 2 years or not. And so that's sort of the main reason that that criterion starts to make sense. Whereas if we're checking things out before we fit a model and we're just relying on the actual data, maybe conditioning on the outcome makes even more sense than conditioning on the features. But none of these are actually possible. Making sure things are zero is difficult. Minimizing them sounds great, but then what's low enough is not clear. So we came up with some more clear approximations. So the first criterion we thought was, well, ideally we wish we could have no mutual information between our features and our protected attributes. So we wish that I of A and X could be 0. We can't get it to 0. Well, but maybe what if we want to put an upper bound on it? We want to make sure that it's less than the information between our X, our features, and our target Y, which in machine learning, we want that always to be as high as possible. So that gives us at least some sort of a bound. Another way we could do this is that we want, not only do we want the mutual information between the protected attribute and the features to be low, we want that to be true for every possible group. So we don't want it to be just unrelated for white people, but the thresholds are swapped for Black people. We want it to be below for Black, for white, for men, for women, for Black women, white men, all of the groups. We want it to always be below. So this is that group-wise uniformly informative beyond the number. So we want every possible prediction we're going to try to make to be better. We want the prediction, the target, the thing we want to be easier to do than the thing we don't want to do. We also propose quality of information. So this is, we just want the problem to be equally easy for all the groups. So this starts to get to look a lot like that independence, right? We want that to be, we want the accuracy to be equal for all groups. We want the performance to be unrelated to the demographics. But this is something we can calculate before we check the model, before we fit the model. So before we're like, oh, I got my model and it's so good, my accuracy is so high and I like it. Let's stop and check what we have there. In order to actually operationalize this, to use it, we have to estimate some distribution. So we don't, the mutual information criteria, mutual information calculation is a function of the distribution of the features, the joint distributions. For tabular data, which is the format a lot of consequential domains use. So the Obermeyer case, it's tabular data. It's not images, it's tabular summaries of information that's extracted from the healthcare records. Banking data largely is that employment applications largely is turned into tabular data. So there's lots of consequential domains where fairness matters a lot, that tabular data works. It's not always images, it's not always free-form text. And in that data, we can use histograms to do that and calculate the information easily. There's known weaknesses to using histogram estimates, though. And what we found, however, is that because we're using relative comparisons and all those approximations, and we're making this relative comparison, that other than like weird edge cases that would be like, obviously that's not a good choice. Like I have 4 classes I'm trying to predict, and I'm only going to bin each feature into high or low. As long as we don't do really degenerative cases, the number of bins changes the quality of the approximation of mutual information. So if we were to analytically calculate it versus not, that does vary. But it doesn't impact the relative comparisons that we're making in our experiments to date. So we have empirical evidence for that, and we're still working on some more details of how robust that finding is. But so far in all of the things we've tested, and we've stress tested things a bunch that doesn't work. So we have this promising technique, And histograms are really cheap and fast to compute. So what we do in a practical application, and this is something that any data scientist can do to a problem before they start fitting it. You think about what your idealized task is, and then you have your data. So either maybe one realized task, or maybe you collect some extra potential target variables that you're not sure which one is right, and you collect a few of them. You build the histograms, calculate the mutual information from those. Once you've got histograms, calculating mutual information turns into a bunch of counts. So it's a quick, easy computation. It's like 3 or 4 lines in most statistical programming languages. You test, check if it meets the criteria, and then you have the choice to either proceed with the problem as it was, tweak it and repeat those steps, or to not build the model at all. And you haven't spent the time or the computational resources required to actually train the model and evaluate a whole bunch of models and optimize the parameters and do all these things. Because we're checking the mutual information, which is sort of the fundamental limits of what any of the machine learning algorithms can do reliably. So it saves a lot of time, and it also kind of, in my perspective, is sort of motivated by, like, once a person's fit the model, like, oh, you spend, the more time you spend on a problem, the more invested you get in it, and the more you believe you have to just figure out how to finish it. So my goal with this is really that we can give someone something they can do quickly, check things, easy to do, and say, okay, well, maybe this shouldn't happen. It gives a data scientist, maybe the data scientist, the junior member of the team, and is a senior person who thinks this should be happening, it gives them something to say, look, this technique isn't going to succeed. And so next we can look at the results that we have. So for the Obermeyer case, we find the same thing that they found, which is that if you compare how well the task can be, so the equality of information criterion, there's a much larger gap for when you use costs as the target than if you use number of chronic illnesses. It brings it really down to almost nothing. There's still some gap, but it shrinks it down a lot. And the rest of our experiments, because Obermeyer data has some problems, the released data has some issues. We're trying to work with them to get the unsanitized data, but the data that's released is they de-anonymized it by generating synthetic data that it's matched on certain properties, but it's not matched on every single property. So some of the calculations don't work. So the rest of our experiments work with a different data set that we're able to investigate more deeply, which is called adult reconstruction. So the adult data set is a very popular data set in machine learning that uses census or data from one of the US Census surveys from 1994. And the adult data set has been sitting in the University of California, Irvine machine learning data set repository for decades. It is traditionally the adult data set it is designed to be a task to predict whether a person makes more or less than $50,000 a year from a variety of features that the survey reports. So there's things like the type of job they have, their income, their capital gains, and a bunch of other demographic features and other things in there. And this data set is used a lot in fair machine learning research because it has a race column and a gender column. And there's known to be, we know there's gender disparities in income, but also the models are differently accurate. There's a performance disparity at predicting the income greater than 50K or not on gender. It's a pretty large gap. So what some researchers, Frances Ding et al. And her collaborators, reconstructed the data set from the source. So they did an investigation through the metadata about the data set. They found the actual survey data that the census records. The census provides all these data with regular open APIs anyways now. And they re-scraped and reconstructed the whole data set. But instead of only having the income column be a greater than 50K, greater than equal to 50K, or less than 50K, they included a continuous variable for income. And their key finding after doing that reconstruction was that the way you formulate the problem, whether you put that threshold at 50K or 40K or 60K or 70, 80, 90, 20, 10, whatever threshold you put that at, the fairness of the models, of a naive model, varies a lot, and the success of their classifiers varies. So this looks like a really good potential case for us to apply our techniques. And so the first thing we looked at is it informative beyond demographics? And so in this plot, the pink line that varies, that kind of is not straight, it's not flat, that pink line is how informative the features are of the target when the target is 10K, 20K, etc. So you see, it's most informative. The features are actually best, most useful for 20K and 30K, and that 50K is kind of in the declining area. And the key takeaway from this plot is that that pink line is only above the line, the orange line for X with A equals race. So the features are more informative at predicting income than race, but they're less informative. So the features would be better at, you're likely to get a better model if you were trying to predict gender than income. If you were trying to predict age, like binned ages, so like 25 to 35 or 34, 35 to 44, et cetera, like bins of ages, or marital status, whether someone is married, single, widowed, et cetera. You can predict, the data has more information, the features say more about all of these demographic variables than they do about income, which explains why we see these large disparities when we fit models, right? And so we're able to detect this in something that takes a few seconds to do, like only a few minutes of a person's time and a few seconds to calculate, which is much faster than the getting a machine learning model and assessing its performance and dividing the samples and computing a bunch of different accuracies, a bunch of different metrics. We can do this with one calculation very quickly. We can see that this is unlikely to be fair. We also then looked at the equality of information criterion on this data set. So are the features equally informative for the different groups within that? And on this criterion, they're actually for age, the disparity is not that large. It's below the information for the task, or above the information for the task, but it's not that different. The task does not vary much for different genders. It varies some for race, varies a lot more for age and for marital status, which makes sense because income is related. Like as you get older, you make more money. Hopefully, we hope that. And marital status changes the household income dramatically. And it can also skew for separated people. It can do weird things in the taxes. So we see that really big gap. There's also a much, much smaller number of separated people. So they're sort of all outliers and we get these weird behaviors in there as well. And then we looked at separation criterion. So if we separate on above or below the threshold, is the information between the features and the protected attribute, does that vary? In this case, again, we see marital status is like a huge gap and it gets bigger with higher income, whereas age, it's gets smaller with higher income. Gender, it doesn't vary that much, and race, it's lowest and it doesn't vary that much. So this put all together, the first one was really the most important, and that might have been enough to draw a conclusion that we probably shouldn't build this model of predicting this because it's going to be biased on these measures. But this gives us a little bit more other pictures. We can kind of pick into different aspects and we can start to see maybe there's ways that would give us hypotheses about what we might want to do instead. So for age, maybe we're like, oh, well, that doesn't matter because we know that age is related to income in ways that we will condition, we will use this differently on different groups of age. But for the other ones, maybe we do care. So it helps you kind of separate how does it work for different criteria. These results, because the plots get hard to read, are only for one attribute at a time, but the technique could work for doing multiple attributes altogether. And we did some of those calculations. They're just very hard to visualize. So we are still, these are early results, so we don't have those plotted out yet. Oh, there's a typo on my slides. But in conclusion, for modestly sized tabular data sets, we have a computationally efficient technique to assess if the problem is well specified enough to actually permit, even enable, a fair potential model. We're limited to modestly sized tabular data sets because of the sensitivity to how you make the calculations increases as you get larger. We're still working on other techniques to minimize that and kind of measure that robustness. And for non-tabular data sets, calculating mutual information is expensive and potentially similarly expensive to fitting a model. So a future direction we're working on is, can we do these calculations while we fit the model as a way to build more robust assessments of preliminary models before we invest a lot of time in optimizing them? So could we fit a model, we get the first thing, what are the results, how fair is it at this, and how much is further optimization likely to help us or not? And with that, I can take questions if there are any.
Thanks, Sarah. If people have questions, I guess put them in the chat. Give people a couple minutes. Here we go. All right, doesn't look like we have any questions, Sarah. Thanks very much.
Thank you for having me.
And oh, there actually is a question here. Wait a second, one just came in. Can you see it, or do you want me to read it? I can read it out. Would it also help to shuffle the data and compare the ground truth MI with the shuffle?
Not sure what that means or what that would look like, in that the ground truth mutual information of an actual data set is hard, right? We don't have an analytical description of the distributions of any real data. So everything in the world, we like to assume it's Gaussian, maybe, or we hope, but it's not necessarily truly that. And so without knowing that the distribution, we can't necessarily calculate explicitly the mutual information, which is part of what makes the robustness checks of how sensitive this technique is difficult to do. We have some results that are, like permuting the features to compare. That could be another way to test the sensitivity, or to even ensure that what your threshold makes sense, right? Because mutual information is not a bounded quantity, and so if you wanted to get a bound or say, like, is this high enough? Is the actual mutual information between these variables more than the true? That would give you sort of a nice, that actually would be a nice sort of first heuristic to check. Like, is this relationship more than noise at all? That would give you a nice bound on that. And you could probably work that into some of the other ways we, some of the other bounds and comparisons that we're making. That would be interesting. We've started some results that my student showed me this week, and I couldn't get the plots into the slides. But we've also developed, related to this, techniques for doing feature selection, and then seeing how well, if we use these criteria to do feature selection rather than traditional feature selection, so it reduces the number of features, and then fit models. What we find is that if we choose a fair subset of the features based on our criteria, and then we fit a naive model and a fair classifier, they get the same performance, both in accuracy and in fairness. So basically, it means that if we tweak our data sets, we modify them, we reformulate the problem to make it more fair, we don't have to add the constraint optimizer on the regularizer or preprocess the data, or well, I guess this is sort of a preprocessing. We don't have to add a regularizer in the classifier. So you could, it also, in that way, in that use case, it ends up saving computational costs, because computing the histograms before ends up being much cheaper than adding a regularization term in the algorithm for certain algorithms that has a high computational cost. So this gives us fairness at a low computational cost, and it reduces the trade-off between fairness and accuracy, which is a common concern of people who are resistant to fairness in machine learning applications.
Okay, that seems to have answered the question. Great. All right, well, thanks, Sarah, and for the talk, and we'll see everybody at the next seminar, probably starting up again in the fall.
Thank you for having me.
Okay, bye.
Bye.